All right, so what we just figured out is that for this function, f of x equals x squared, let's put the f of x there. All right, there's a magic point. That point is 2 root 3 over 3. That point has the property that when I evaluate f of that point, f of 2 root 3 over 3, I get 4/3. So I have the point 2 root 3 over 3 4/3 is this point right here. And when I make a rectangle based on that point, then the area of the pink rectangle is exactly the same as the area of the green curvy shape, right? The area of the green curvy shape is 8/3. The area of the rectangle is 8/3. So it turns out that this is a property that every function has, and this has a special name. It's that 4/3 is called the average value. The average value of x squared over the interval 0, 2. So I want to talk a little bit about the meaning of the average value. Average value in and of itself is important and significant. What it really comes down to is that this 8/3 is our integral of the area. So I mean, one way to say it is that the f of this magic point, let's call it f of c, all right, times the length of the interval, which is b minus a, is equal to the area of the green curve, right? This is the area of the rectangle right here, because it's f of c, f of the magic point, times the length of the interval, which is b minus a. You could think of this as the b minus a over 1 formula, where n equals 1, right? So this is just the pink rectangle, area of the pink rectangle, and that's equal to the integral from a to b of the function. All right, and so we still don't really have a way of calculating this. For now, we're just using the symbol to represent that unknown area. And we're going to get to be able to evaluate it today. All right, so that means that that magic point f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. And this, again, is what is called the average value. So this is called the average value of the function f over the interval from a to b. All right, so I guess a couple of things about that. One is, this point turns out to exist somewhere, regardless of what the function is. So that is a fun theorem in your book. It's on page 288 of your textbook. It's chapter 5. It's called the mean value theorem. We don't just mean value theorem, but this is mean value theorem for integrals. We did the mean value theorem for derivatives. So the mean value theorem for integrals says that, where's that theorem? Page 288, I said? Yeah, here we go. Page 288, here it is. The mean value theorem for integrals. Okay, they said for definite integrals. All right, so you need f to be continuous. So f continuous on the closed interval AB. By the way, the mean value theorem for integrals, you will be happy to know, you do not need to memorize. Nobody ever asks about this for some reason. But it says there exists a point C. So there is a point C, and that C is in the interval AB. It's in the closed interval somewhere, such that f of C equals 1 over b minus a times integral a to b of f of x dx. A seemingly silly thing, but what it's really saying is there's always a magic point where you could evaluate the area using one rectangle and have that area be exact. Now, the drawback again is we don't know where this point is unless we can do this integral. So we can't use the point to get the integral. It's generally going to go the other way. We need another way to evaluate the integral, but this is going to give us an important key to that. But I want to point out that right away that the f of c has an important use in its own right. So let's talk about first motion. So remember our initial considerations that led us to even think about these areas was if I have a velocity curve, so I have v of t on this axis and t on this axis, and then I have a vehicle that's doing some complicated thing, starting from rest, accelerating slowly, accelerating faster and faster as the engine reaches its optimal power, then slowing down as we reach a speed limit or desired speed, and then gradually putting on the brakes so the vehicle slows slowly, the brakes engage, the velocity drops more quickly, and then we let off the brakes a little bit so that the vehicle slows gradually to a nice stop. Okay, so that's a more realistic velocity curve for a vehicle. Now, the area under the curve is the distance traveled, right? So the integral from A to B of v of t dt equals distance traveled, all right? It's really displacement. We're talking about positive distances for now, positive velocities. Now, in that magic point, there's a magic point where I have a rectangle that has the same area as the curve, all right? That rectangle has the same area as the curve, but the velocity is constant. So what that means is that the distance covered in that time by the complicated shape is the same distance I would cover if I constantly traveled at a certain velocity and then stopped. So it's a constant velocity that covers the same distance in the same amount of time as my complex velocity curve. So that's why it makes sense to call it the average speed of the vehicle. All right, but it doesn't have to be a rate of change. We could also talk about other things like, let's say we had hospitalizations due to COVID. All right, so on this axis, we're going to put COVID hospitalizations. And on this axis, we're going to put time. Okay, so we have not very many people hospitalized. Then all of a sudden, we have a ton of people hospitalized. Then a bunch of them go out. And then maybe there's a little second wave. And then eventually, nobody's hospitalized. We're really hoping to get to that point. Okay, so the area under that curve is going to be the total number of people who have been hospitalized over the entire time. All right. And then when I find that average rectangle whose area is the same as the average green rectangle, what that's going to be is my average hospitalizations over that time. Average hospitalizations, okay? So it really is like an average rate of any function. So I can take any complex function and say, I said average rate, but that's not correct. It's the average value. The average value is going to be the average number of people who are in the hospital. In this case, I called it average velocity because the function is velocity. So if my function is velocity, then the average value of that function is an average velocity. If my function represents COVID hospitalizations, then my average value is the average number of people who are in the hospital. All right, so that's the value of average value. It's a valuable thing to be able to do in and of itself if you knew how to get that. But we don't yet, but we're about to.